Hello students, welcome to today's lecture. So we are going to discuss cell momentum balances and boundary conditions. Okay, so what do you mean by cell momentum balances? Basically, we take a thin control volume, let's say dx, dy, dg, right? And we do momentum balance over that thin volume. Okay, so what is the purpose of that? So we want to uh, we want to find out what will be the velocity profile of a given problem, what is the shear stress profile for a given problem. So we are going to basically find what is the maximum velocity, what is the mass flow rate. Okay, so as I told you earlier, there are different levels of study: macroscopic, microscopic, and molecular level. So you can say here we are doing basically microscopy analysis. Fine. So we'll be studying various problems like falling film, okay, flow over a plate, circular flow, flow of some fluid inside a circular pipe, flow of fluid inside a annulus, and we'll obtain the various values like velocity profile, maximum velocity, mass flow rate, and so on. Okay, so let's begin. So I already told you about the types of flow. We have laminar flow and the turbulent flow. So here is a diagram given here. So if the fluid is flowing in a pipe and you are putting some dye to see the flow pattern. So you're putting some tiny particles, which you can see with naked eye. So you can see in this flow we have very orderly flow of the particles, or you can say dye. Okay, but in case of turbulent flow, you can say it's a random motion, right? There is chaos here. It's not very orderly. So this is turbulent flow. Okay, you can check on YouTube uh, how this the flow is seen. Okay, you can check on YouTube as well. Okay, so we'll start with momentum balances. Fine. So cell momentum balance is nothing but just balance of moment, or you can say conservation of momentum, or you can say force balance, right? So for any balance, we have general equation is like in minus out, right, is equal to what? Accumulation. Okay, for a general mass balance, we have this general formula: in minus out is equal to accumulation. Okay, now the thing is, we are in cell momentum balances. We are basically doing steady state balance. Okay, steady state. You already know in steady state there is no accumulation. Fine, or that means in is equal to out only. So in is equal to out. So in this chapter, cell momentum balances, we will basically study steady state balances. Fine. So that means here accumulation will be zero, right? So we'll see. Okay, so the basic general cell momentum balance equation is like this. So zoom a little bit. Let's transfer here. So rate of momentum in. Okay, I told you in minus out, right? So in rate of momentum in minus rate of momentum out, right? So if you consider this part, this is rate of momentum in minus rate of momentum out, right? So there are two modes of transport: molecular transport and convective transport. So it is first considering convective transport, right? So rate of momentum in by convective transport minus rate of momentum out by convective transport, right? Similarly, you have to consider the molecular transfer. So you have a plus here. Again, same here. Rate of momentum in by molecular transport minus rate of momentum out by molecular transport, right, is equal to no accumulation here. That's why it's 0 here. So there is no accumulation of momentum. Okay, because we are doing steady flow. Okay, obviously you can study the unsteady flow and you can make the derivations as well, right? That is a little bit complex, so you have to know finite differentials formula. So we will not be studying unsteady state problems in this course. Okay, we'll basically deal with steady state problems. Okay, now you might ask, what is this? Okay, this is actually your external force. Okay, so there has to be some external force because of which there is a momentum transfer, right? So let's say we have a force of gravity acting on the system. So there is a force of gravity. Because of that gravity there is some flow, so that we have to consider that force, right? So we have to add that external force here. Now if you see, we are basically doing summation, force, summation Fi equal to 0. This is because this is nothing but sum of the forces. How? Because the rate of momentum is nothing but what? Force, right? It is Newton's second law. The rate of change in momentum is directly proportional to force, right? And rate of change of momentum is nothing but mv dmv by, so rate of change of momentum is nothing but dmv by dt, and since m is constant you can take it out, right? So dv by dt, that means dv by dt is nothing but acceleration, so force into mass into acceleration, so it is nothing but force. So this is nothing but force arising because of the convective transport, right? So this is a general equation. Okay, with using this equation only you have to do the cell momentum balance for all the problems, so you can remember this. Okay, now there are few steps to how to solve a flow problem. Okay, you can say viscous flow problems, because if there is no viscosity then there will be no momentum transfer, because you can see tau y x is equal to minus mu dv x by dvy. So if it is not viscous, if the fluid is not viscous, it does not offer any resistance, so there is no point of momentum transfer. So we are solving viscous problems, okay, so which have some viscosity. Okay, so what are the steps? These are the basic steps you can follow to solve any problem. So first you have to identify the non-vanishing velocity. So if certain flow is in this direction, that means according to the coordinate system, let's say this is in z direction, so this fluid is flowing in z direction, so v is not 0, right? But you can assume vx or vy as 0 because there is no flow in perpendicular directions. Okay, so you have to find out which is not, which in which direction there is a flow and it is non-zero, in other directions it is 0. Okay, so you have to identify this term, non-vanishing term. Okay, now you have to write a momentum balance, a above formula. Okay, as I told you earlier, the equation you have to use, okay, over a thin cell perpendicular to the relevant spatial variable. So you have to use according to the problem which direction you are doing the balance. Okay, so you can, then you have to take limit that thickness of the cell will be 0, then you can get, if you apply limit, let's say delta x tends to 0, and you have this delta y by delta x, so this is nothing but dy by dx, right? So you have to take use of this using limits. Fine, then you will get this differential equation. Okay, so next step will be Okay, next step will be your to integrate that differential equation. So if you integrate that, you will get momentum flux distribution. You will get tau x is a function of something. Okay, x or y, it can be anything. You'll get this. Now you have to insert Newton's law of viscosity. If you insert Newton's law of viscosity, then you will get something like this. So you can get the velocity profile, right? You just again integrate it, so you will get Vx and function of something, right? And some constants, right? So you'll get velocity distribution if you integrate this. Now you can, if you once you get the velocity distribution, now you can get other parameters as well. Sorry, side right. You can get maximum velocity, right? You can get average velocity. You can calculate the force on the solid surface. You can calculate the mass flow rate, okay, and so on. Okay. Now you can see next we have boundary conditions. Okay, what do you mean by boundary conditions? So, for example, just delete this stuff. So boundary conditions, BCs, you already know while solving, you know, integral equations, you have to use boundary conditions. So let's say we have uh, d vy dy. D is a function of y, and you have y, right? So if you integrate this, you will get something like function of y and some constant, right? Integration constant. Now you have to find this integration constant. So you cannot find integration constant without given initial condition or some boundary conditions, right? So you have to put like v is equal to 0 at y is equal to some value, right? So let's say v is equal to 0 at y is equal to 0. So if you put these values in this equation, you will get c equal to 0. Just for an example, okay? So that is the integration constant, and you found out using the boundary condition, okay? So some the boundary conditions will not be given in the problem. You have to assume appropriately. For example, what will happen if we have a boundary condition at solid fluid interfaces? So suppose we have a solid surface and fluid is flowing in this direction. So this is fluid and this is solid, right? So what is the interface? This point, the intersection between the fluid and the solid surface. So at this point, you can use boundary conditions directly. Like if the fluid is flowing in this direction, let's say Vx, so Vx will be equal to 0 at this surface. Okay, that is called no slip condition. Okay? This is called no slip condition because the fluid in contact with the solid surface, which is not moving, the solid surface is stationary, so definitely the fluid cannot slip over this, right? So it has to be the fluid at this point will be stationary as well because it is a no slip condition. The fluid will not slip over this. Okay, if it is frictionless, it will slip, but it is not frictionless because it's not possible because the solid surface will not be very smooth, right? So there will be some friction, so it will not slip. So the fluid will also be 0 at that point. So that is called no slip condition between fluid and solid. Okay. What about if you have two liquid phases? This is liquid, it is also flowing. Here also it is liquid, some it is flowing, right? And they share some boundary here. So from fluid-fluid interfaces or liquid-liquid interfacial plane, right? Or at constant x. Right? So at that point, you can say that the pressure is and tau xx, tau xy. Those are like continuous. Right? They are equal for this as well and for this as well. At this point, these shear stresses at those points will be equal. Okay, it is called continuity or no slip condition because if the two fluids are moving, definitely that then at the point of contact there will be no slip. So if one fluid is moving, then another fluid will also move if it is in touch with that moving fluid. Okay. Thirdly, we have liquid gas interfacial plane. Suppose we have a liquid here flowing open, for example, the liquid flowing in reverse. So the in reverse the liquid flows, right? At the surface we have air and liquid interface, right? So at this point, what boundary condition you can take? So it is saying that if you take a plane of constant x, then you can write tau xy and to be 0. You can easily set this equal to 0 because the gas does not, you know, the viscosity of gases is very less, so you can easily take 0. Or the gas side velocity gradient will not be very large because the viscosity of the gases is very low, right? So you have to keep in this boundary condition in mind, okay, so that you can directly take appropriate boundary condition while solving problems. Okay, so in this chapter we are basically solving problems only. Okay, we'll not be doing, you know, derivations, but the momentum cell balance itself is a derivation. You have to follow those steps I mentioned to get the velocity profile, right? So the you can directly solve the problems and you do the appropriate derivations. Okay, so this is our first problem: flow of a falling film. Mm, Suppose you have an inclined plane, you put some drops of water. So what will happen? The drop will flow along this plane, right, at an angle. And who is causing this liquid to flow over the inclined plane? Definitely, this is force of gravity, right? Mg. This is the external force here in this case, right? So we can now easily, you know, derive the velocity profile using momentum turbulence. So you first understand the problem. So we have a reservoir, right? We have something like tank here. It is stored, and the once the fluid level is increased up to this, then definitely it will try to flow out, right, in this direction. And this is some plane at an angle beta from the y, from this vertical axis. We will see which axis to choose. Okay, and this length is L. Okay, this is length of the inclined plane is L. Okay, now there is one important thing. Now since, see here, after the plane is finished, you can see the flow is not, you know, laminar. It is like something turbulent, right? It is spreading out. Similarly, at the entrance point, there will be some chaos here, some disorderly movement, kind of turbulence, right? So you have to assume that the, you know, your whatever you're doing the balance, you're doing over this length, and you have to ignore this entrance disturbance and exit disturbances. So you are basically doing the momentum balance over this area only, right? Because once this, if you consider these disturbances, it becomes turbulent flow, right? There are some advanced courses to study turbulence flow, but in this course we'll only deal with laminar flows. Yeah. So you have to make appropriate assumptions. Fine. So now because of gravity, the liquid will flow over here. Now this is called laminar flow, right? It is a falling film. So it is a very film. Film in the sense the thickness of the liquid over that plane will be very less. This thickness will be very small, like some delta. It will be very, very less. It will be almost 10 to 0. Okay? That is all falling film. We are talking about falling film. Film is very low thickness. Okay, so this layer of the liquid will be very thick, thin. Fine. Okay. Now, just once again, we'll see more clearly. Okay, you can see here now what you saw in the last diagram was this. That was the side view, right? If you see the top view, now you can see this is the top view here, right? This was the L, right? Length L in this direction, right? This is the width. What is width? So it is given as W. What is the thickness? Delta X. Because you're doing a thin shell balance, right? You have to have a small thickness delta X. Okay. Why delta X in this direction only? Because fluid is flowing in this direction. The direction of the momentum transfer will be at the perpendicular. So in this direction, right? So as I told in the steps, you have to take a thin shell balance around this perpendicular direction, along the 90-degree perpendicular to the flow direction. So we are taking finite thin element in this direction because the flow is in this direction. So perpendicular to this direction will be this. Okay, fine. So now this was the problem, right? You have to find how the thin film will flow over this plate. Okay, so now we have to do balances. Okay, so now see, in we have what? Phi momentum in minus momentum out plus force, external force, equal to 0. This is rate of momentum, sorry. So see, you cannot take only tau because we are talking about rate of momentum in and out. Combined momentum, you have to include shear stress as well as convective molecular transfer, as well as pi. Molecular transfer was pi and convective transfer was rho vv, right? So you have to take both components, right? So I will use pi combined momentum transfer equation, pi in minus pi out, right, equal to plus force equal to 0. Okay, so in minus out. Now in how many directions there will be your momentum flow, right? See, so you have, see, the fluid is flowing in this direction, right? That means the fluid will not flow in direction as well as in this direction. So the velocity will in this direction will be 0 and this direction will be 0 and this direction it is non-zero, right? Remember that previous first step, you have to identify non-vanishing velocity direction. Okay, now since this is rectangular, this thin plate is rectangular in shape, so you have to use rectangular coordinate system because it will be easier to describe this problem in rectangular coordinate systems, right? You can use cylindrical coordinates, but it will again unnecessarily be complicated. Your first job is to make the problem simple. So if you take rectangular coordinate system, the problem is half solved, right? It becomes very easy to handle the problem. Okay, so in this case, since it looks like rectangular in shape, the thin cell, right? So we will go for rectangular coordinates. Okay, now you choose the coordinate system, right? I mean direction of the coordinates. So in this problem, it is taken as this as z direction, this as your x direction, and along this direction it is taken as y. Okay, if you see, it is a right hand rule, right? Sorry, this direction is y. Okay, now you can apply the right hand thumb rule. You can see x cross y will become 0. So this is positive z, this is positive y. this is positive x, right? Don't take positive x in this direction. Obviously you can take, but then the z will be in this direction, which is against our problem. So we have to make the thing simple. So the flow is in this direction, so it is taken as like this. Okay. You could have also taken this as x, this is this is like, yeah, this is y, and this direction is z. It's your choice. Okay. So to flow along with this problem, right, with this solved problem, so we'll follow the same coordinate system as this problem, as this solution. Okay. Okay, so we'll start with momentum balance. Okay, it will be easier to follow this, this diagram itself. Okay, let's see. So in this direction, in this z direction, what is the rate of momentum in? So momentum is entering in at this point, right? Yes or no? Okay. And it is going out at this point. Fine. So we have to find phi xz, where it is entering at this point, right? What is this point? Z equal to 0 minus phi same xz, what is going out at this point, that is z equal to length L, right? Similarly, you have to see in this direction. Let's say see in the y direction. This is your y direction. So in y direction you have to consider this one, phi yz at y equal to 0, because it is in point, minus phi yz at y equal to w, right, out. Similarly, in x direction, what we have, phi xz at what point? At x point. This is the in, this in point, minus phi xz at out point was x plus delta, because you have taken thin film in the direction perpendicular to the flow. Flow is in z direction. Flow is in z direction. Then perpendicular direction is this, right? So you have to take a thin. You have taken thin cell in this direction, right? This is delta x. Rest remains same, y and z. Okay. So now you might ask why phi yz, why phi zz, and why phi xz. It could have been other, right? Other values. Then why? So you can see the problem. Once you choose the direction of flow as this z, so vz is showing this, then what will be the momentum transfer, right? What is the plane? So if you consider this cross section, the entry point, this is nothing but z plane, right? What is the normal to this area? That is z direction. So z, and what is the flow direction? Yeah, this direction, right? Z, vz. So dz by dz, right, around this gradient, because this is a normal direction. So we have taken phi z for this case. Similarly, if you consider this surface, what is the surface normal direction? So this is in x direction, right? And for what is the flow direction? In this direction, that is z. So v is flowing in this direction. So what will be the gradient? dvz by dx. Now you can see here it will be what? Dz comes here and x comes at phi z. So you have to consider phi z, xz, right? Similarly, there will be phi z x those stuff, but these values will become zero because there is no flow in this direction. Oh, sorry, yeah, there is no flow in vx direction because the flow is not happening in this direction. So this will be zero. Okay. Similarly, y phi yz. So what is the area here? So we consider this area, right? This is in y direction. What is the area normal? Y, right? The flow is happening in z direction. So the vzy, it will be something like dy, right? This is best represented by phi yz, right? So you have to take this value. You have to ignore other values because those values are zero. Obviously, phi zy and phi yz will be symmetric, so it will become equal. So you have to consider any one appropriately. Okay. Now you have understood why only certain values are taken. Okay, now let's do the balance here. Okay, so first, rate of jet momentum across the surface at z equal to 0. That is nothing but phi zz, right? Phi zz is the combined momentum transfer, molecular transfer plus convective transfer at z equal to 0. That is in. This is in. This is out, right? But here it is multiplied as w delta x. Why? Because this is what I told you. This is momentum flux, right? Pi is nothing but momentum flux. So if you multiply with area, which is w delta x, then what will be the thing? Then it will be momentum per unit time, right? Momentum per unit time is nothing but force. So we are doing force balance. Okay. So at z equal to 0, this is the case. At z equal to L, at z equal to L, we have this one, right? Out. So it is same thing because what is the area? W delta x, right? So this is the area. This is W. The length is W, or which is W, and the height is what? Sorry. Yeah, this height was delta x. So W delta x, the area of this one, right? It will be same, right, for out as well as in. So it is same for this in and out. Okay, now this is done, and again rate of jet momentum across the surface at x. So in this direction, what is the momentum transfer rate, right? So I told you it is phi xz, right? So in point is at x and out point is x z x plus delta x, right? And you have to find momentum rate, so you have to multiply with area. Then what is the area of this surface, because momentum is transferred across this surface? So the length is L and the width is W, so LW, right? So both the cases, this is in, this is out, right? And there is no momentum, you know, momentum transfer in y direction. Why? Even if you take this value, now see this part, what is Vy Vz? Vy is 0, right? There is no flow in the y direction, so definitely this term becomes 0, right? What is tau yz? Tau yz is nothing but minus mu Vz by dy, right? Yes or no? So tau yz is nothing but minus mu dvz by dy. Now Vz is not 0, but Vz is only a function of x. Why? Because according to Newton's law, the momentum is only transferred in the perpendicular direction, right? So it is in x direction. It is changing, transferring in the x direction, right? So it is not, Vz is not function of y. So if you So Vz looks like constant with respect to y. So this term is 0. So this whole term will become 0, 0 plus 0. Right? So that's why it's not included here. Okay? So now only left with the force. Okay? So to calculate force, you have to add force, right? mg. Okay? But our coordinate system is not in direction. Fine? So flow is in direction, right? Rate momentum is in direction. So you have to, because of flow is in direction, the force causing it should be in direction, right? So since force is given in this direction, you have to take the component of this force in this direction, because this force is causing to flow in this direction, right? So if this is beta, then what will be the component of gravity in this direction? That is nothing but g cos beta, right? G cos beta. So basically mg, right? So m into g cos beta, because g is always in this towards downward, right? But the flow is happening here, and because of the component of gravity in this direction, so you have to take g cos beta. Now, what is the mass of the fluid of this thin element? So, generally in momentum shell balancer, you'll be given the density of the fluid, right? So, mass is nothing but density into volume, right? So, you have this formula, and you have to find the volume of this thin, shell you have taken. So, what is the volume? Definitely, LW will be this area of this, the LW, and the thickness delta x. So it will be LW delta x, rho g cos beta, right? So you're done, right? So you have calculated all the factors, right? I think it's clear up to here. You might be wondering why you have taken phi zz, why you have taken xz, right? You remember the first step. You have to first determine the non-vanishing velocity. I told you the flow is only in this direction. Vz is not 0, and only the Vy and Vx is equal to 0. So definitely you have to consider only those terms which have, you know this z in the second part, right? It can be x, it can be y, it can be z. Since velocity is only in z direction, so these three only is possible, right? Rest, if you have yx, or suppose xx y z, and this remains, this is not possible. Why? Because there is no flow in the direction of x. Because even if you take this, it will become 0. How? So let's suppose I take this one. So phi xx, which means you have to take the molecular stress, that is pi xx, plus convective transfer, that is rho Vx Bx hoga. So this Bx is 0, I already told you. So this is gone. What about this? Since it is a normal direction, so you will have pressure plus tau xx, right? Again, tau xx is nothing but minus mu dvx by dx. Again, vx is 0. So this becomes 0. And regarding this pressure, right? So where is the pressure coming from? See, pressure is coming from because of this atmospheric pressure. You can say atmospheric pressure P here, right? At the top, and at the bottom this pressure will be this plus pressure of this fluid. The above fluid is exerting some pressure on the surface, right? The weight of the fluid will be applying pressure. So that term. So P is only function of what? In x direction, right? So even if you only this term is here, then in minus out it will become 0. Okay. So in this case, pressure is function of x. It is given in the problem. I'll show you. Yeah, here you can see here. Therefore, it's reasonable to postulate that Vz is the V function of V. Yeah, I have to tell you this, that V flowing is this direction, but momentum transfer is in direction. So Vz is a function of distance, right? Why? Because the if the velocity is close to the wall, it will be zero. If it is away from the wall, it will increase. It will be max at the away from the wall, right? So definitely it is a function of x, and Vx is zero, Vy is zero, and further P pressure is function of x, right? Why pressure function? I told you, because the fluid will exert the above liquid will exert pressure on the bottom liquid, right? So the pressure of this fluid, part, this part will exert some pressure on this top. So it's only function of x direction. Okay. So I think this part is clear, right? This part is clear. So now you just put in rate of momentum in minus out formula. So you'll get this one. How? So if you see here, so rate of momentum in which direction is this? In z direction, across the surface x, because kind of shear one, right? And z momentum in z direction, right? And there is no momentum in uh, y direction. I already told you. So, and the force, right? So rate of momentum in plus rate, all the rate of momentum in minus out, right? All directions, and this plus force equal to zero, right? Now you have to again simplify this, because okay, now we'll see. So first we'll attack this one. Okay, so phi xz, which is phi xz, right? If you see this term, what is this? This should have the molecular stress plus convective one. So here, this is convective, this is molecular. It should have been pressure, right? No, there will be no pressure in this, because this is purely stress. Because only if these two indices will be same, then only there will be pressure. As is here, it will have pressure because it is z, right? Only because pressure acts in or normal direction as only. Now this term becomes zero because Vx is zero, right? But this term will remain here because this will give you minus mu dvz by dx, and vz is definitely a function of x, so it will not be zero. So for phi xz only this term remains, right? Where is phi? Yeah, here only this tau xz minus tau xz at x plus z will here. So this will, if you simplify this, so this will become Lw tau xz at x in minus tau xz at out x plus delta x, and Lw will be there. Fine, this term is clear. Simplified, it will be because this. And what about the second term? We'll see this one, right? See, so phi zz. So what is phi zz? Phi zz will be, this is combined molecular stress, combined stress tensor. That will be your molecular stress plus convective stress. So it is nothing but, since this is indices 2 and there will be pressure here, plus tau zz, right? Then plus convective 1, this is molecular stress, this will be vz, right? Okay, so this will be there, pressure will be there, this will be there, and this will be there. Okay, for both at z equal to 0 and z equal to L. Okay, right? So you can see in another page we have that. So it is exact definition of derivative of this. So you can just you can do directly here or after making everything zero, right? So here it has done firstly this taking the limit. So if you take the limits, right, before that it is dividing both sides with this LW delta x. So here delta x becomes here, stays here, here L will stay because here it was W, W delta x, right? So W delta, if you divide by LW delta x, so W delta x cancels out, only L remains. So here it will be only rho g cos beta, right? So this is nothing but differentiate dou phi xz by dou xz. Okay, this is definition of limits. You convert limits into differential equation, or no, yeah. Then again here, but here we don't have any delta term, finite term. You cannot take it limit because L is constant, a finite value. So there is no limit here. So it is simply like this. Okay. Now they have simplified here. You could have done this first and directly put it, or the vice versa. It's your choice, whichever is convenient for you. Okay, now only we have phi xz and phi z equal at 0 and this. Okay, now you see this one. So phi x is nothing but tau xz plus rho vx. This becomes 0, I told you, because vx is 0, right? So this will only remain with this one. This will become 0. So here it's written the same thing. We see that since vx is 0, rho vx vz term in this equation is 0, right? And there's something which I haven't taught you. See, if you see this formula, so this is sorted. Okay, you next move on to phi gg, right? That is the definition will be p plus tau gg plus rho vz vz, right? Okay, so this will remain, right? This will remain because it is function of x. And this definition, you might ask why tau gg is equal to minus 2 mu d dou vz by dou z, right? Why it is 2 here, right? So I will explain the next class because I somewhat forgot to tell you about this in the previous class. Okay, so I will tell you. For now, just assume it is minus 2 mu dvz by dz, right? I will make a separate video over this, why it is like this, minus 2y comp. Okay, so this is there and this is there. Now what is saying, the term, see, this will become 0. Why it will become 0? Because vz, velocity momentum only transferring in x direction, right? So vz is only function of x. It will not change in y direction. It is assumed, right? So velocity profile will not vary in y distance or in z direction or only in x direction. But you might say that, yeah, the fluid is flowing in z direction, but why it's not a function of z direction? Because see, initially it is definitely a function of z, because with time, let's say I start here, the fluid will try to flow, right? Slowly it will come up to here. Okay, so with time there it will be a function of z, vz will be a function of z. But I told you we're only doing steady state balances. We're saying that at infinite time, when the system becomes stable, there is no dependence on time, right? At that point, it will not be a function of z. Okay, so we are doing only steady state balances. We're not doing unsteady state balance. If you do unsteady state balance, then definitely you have to take this into account, because vz will be a function of the z direction, in the direction of flow. But in this case, we're directly doing after finite time, when the system is stable, there is no change with time. Then at that point, everywhere the Vz will be same. So at steady state, the velocity Vz will be same at every point. So that's why it's not a function of z. Okay, so this term will become zero. In next problem, that is flow through the circular pipe, there you also see that we are assuming steady state balances. So the v, whatever velocity is there, it will not be a function in the direction of flow. Okay. So this term will not be, this is zero, this term will not be zero because Vz is non-zero, right? However, so we have here, so this formula is now P plus rho Vz, right? So phi z at j equal to 0 is what? P at P, right? P plus rho Vz at z equal to 0, okay? Minus P plus rho Vz z equal to L, okay? Now these both are same because Vz is constant, right? Vz will not change, is not a function of z. That means Vz at z equal to 0 at z equal to 0 will be same as this. So both will cancel out from this and this. Again, P is not a function of z. It is only function of x in the x direction, right? That means it will also cancel out. That means these things will become zero, right? Because of the subtraction. So only left with, because phi xz is nothing but this one only, tau xz. So you have put here. So from here to here, right? Everything will become zero. Only this is left and this is left. You have got the equation, right? So you have found the equation. Now simply you have to do the integration. So now do the integration of this equation. If you integrate it, then what you will get? Tau xz equal to rho g cos beta x, right? Plus in constant of integration. Now you have to find c, right? If you see the diagram, where's the diagram? Okay. You have to find out where shear stress will be zero. Can you find out where the shear stress will be zero? So the shear stress is zero at this point. Why? I already told you about the boundary conditions. If you see in this one, no, not in this one. Yeah, here. At liquid gas interface, this term xz is taken to be zero, right? Liquid gas, because this is falling film, right? This is the liquid film and this is air, atmosphere. So this is the interface, right? Here it is interface between liquid and the air. So that means you have to take tau xz equal to 0, right? So you have got your boundary condition. So you have got your boundary condition. So tau xz equal to 0 at x equal to 0. Remember, we have origin at here in at this point. So at this interface, that is x equal to 0. So this tau xz is 0. So if you put this term becomes 0, this is 0. C 0 equal to 0 plus c. So c is 0, right? So you have got, so you have got only this. So constant of term is 0, right? Now you have to put the Newton's law. Newton's law of viscosity counts because your stress is related to the velocity with this relation, right? So you simply put this in here and rearrange it. So you will get dvz dvx minus mu terms goes here. So this becomes, right? Now I can integrate it, right? If you integrate it, so Vz becomes, this will become x squared by 2 plus constant of integration C2, right? So this is what you get if you integrate it, this one. Right now again, to know this C2 value, you have to use boundary condition. Now you have to say where the Vz is 0. Now we have a, so this fluid is flowing here, and this is your solid surface, and this is your fluid, right? So this is your solid fluid interface. We already told in the first, the I will show you, otherwise you'll get confused. Okay, so if you see it in this, what is going at solid fluid interface, the no slip condition, so velocity becomes 0. The velocity equals the velocity with the solid surface, right? Since the solid surface is stationary, so the velocity of the solid is 0 in this case. So the fluid will also attain 0 at the wall, right? So that means, what is the boundary condition we have here? So that means Vz is 0 at what? At x is equal to delta. If you take the thin film, this is your origin, right? This is, since this is your z, this is x, so at this point, this is your thin thickness of the film, right? Let's say it is delta. So at 0 is equal to x is equal to delta, the Vz is 0. So you just put it, so C2 you will get what? Just put x is equal to delta square, right? So C you will get, just move it on this side, so you will get rho z cos beta 2 mu delta square, right? So C2, if you put this value here and may simplify it again, so see, I have taken the thin film as delta, and you just put it, you will rearrange it, you will get in this term. So if you rearrange, so you have got the velocity profile here, right? This is your formula. If you see, if you closely see, so Vz as a function of the variable x square. So x square means what? It is parabola, right? X means if you have x only, then it will be linear. Let's say in case of shear stress, what was the formula? What is the formula in case of shear stress? You see here. So shear stress xz is a function of only x raised to the power 1. So this linear, right? So shear stress, if you plot the shear stress, you will get a linear line. However, if you plot this one velocity, then you should get parabolic curve, because this is x square, right? So now they have plotted here. So at x is equal to 0, shear stress is directly linear, right? At x is equal to 0, it is 0. So 0. As the x is increased, the shear stress value is also increased. So it is denoted by this line. So this line means higher value. So shear stress is highest at the wall. Or you can say the force at the wall is the highest for this one. At this point, the force of the fluid on the wall will be the highest. So this is the thickness delta. And velocity is 0 at the wall, right? And it will increase as a parabola function. So this is what, so this is the velocity profile. So in exam you have to plot it like this. Okay, now just think, if I put another wall here, what will happen? If I put another wall here, what will happen? So again it will assume some parabola. So that is the thing. If the fluid is flowing between two walls, it will get a parabolic line like this. Because there is no wall here, so we have only half parabola. Okay, we'll see in the flow through a pipe, you will definitely obtain like this parabola. Okay, so we have got the Vz. Okay, so that was your purpose, to plot shear stress and the velocity profile. Now you have got it. Okay, now next part was to calculate various terms, right? So first term we will calculate the maximum velocity, max velocity, so V max, right? You have already obtained the formula, right, for velocity. So you can clearly see, if you put x is equal to what value, x is equal to 0, then you will get V max velocity, right? Why you will put x equal to 0 to get maximum velocity? If you see here, it is also from common intuition, because at the wall the velocity will be 0. If it is away from the wall, which is in this case x equal to 0, then you will get Vz as a max. So you can see here the line is max here, so it is the magnitude of velocity here. So it is maximum at x equal to 0, right? This is the origin point. So to get the maximum velocity, simply put x equal to 0 here. So 0 by delta is 0, 0 square 0, then 1, just simply this value, right? So it is, so your maximum velocity is this. Okay, now average velocity, how you calculate average velocity, right? So for average velocity, sorry, okay, so average velocity is denoted by this one angle bracket. So is that, so simply it's nothing but some kind of this formula. If take all the small areas of velocity a1, b1, let's say I v I is equal to some, like, it's like dividing the whole flow cross section with small areas ai, and divided by total area. This is your average velocity. This is called weighted average, right? You know, already know weighted average. In statistics, you multiply with frequency sometimes, right? But in this case, you will multiply with area, because the velocity will change with the area, right? Why it's changing with area? If you can see in this problem, so this part has different area of cross section to flow cross section. So it is different in different regions, right? So you have to integrate over the area. So this is the formula, but if summation is nothing but integral, right? Infinite sum. We already studied that integration is a infinite sum. Okay, this n tends to infinity, then it becomes integral. So it is nothing but, v z dA and dA total area, right? So in terms of, if you write it, if you write dA is nothing but what? dA was in the flow cross section area, this cross section area, right? Because fluid is flowing in this direction. So this, if you take small area here, this is nothing but in this dy and dx, right? So dx dy. So you have taken it. So it is nothing but area integral. So you have to dx dy. So what is the dx limit? 0 to delta. What is the y limit? This is 0 to w. So same thing here. So again, same, you have to put here instead of a. So this is the average velocity, how you find. Now dx is nothing but delta, right? At the bottom you will have, if you integrate this, first you have to integrate this part, so that will become delta, and then you have to integrate dy from 0 to w. D is constant, it's not function of y, so d comes out, so it will be w minus 0, so w. So the simply at the bottom this value will be delta w. What about here? So first see, vz is a function of x, right? So this you can keep it. However, if you integrate vz dx with respect to y, then it is nothing, it is constant with respect to y. So you can easily integrate dy separately. So 0 to w dy, that is nothing but w. So right, so w comes here and we have w delta here, right, and 0 to delta only this, because vz is a function of x. So w cancels out, it is nothing but 1 by delta only. So if you integrate, so vz was, you already found out, right, this into 1 minus x squared. So you have to integrate this. This is constant, this part is constant, so it goes out, right? Okay, delta was there. So if you take it out, then again you have to differentiate chain rule. You have to apply chain rule here. Okay, so if you integrate, you will get this formula, and it is nothing but what is bz max, rho g delta square cos beta by 2 mu, but here it is 3 mu. So it just multiply it 2 and divide by 2, right, and you collect this term here. It is nothing but vz max. So 2 by 3 vz max. We have found average velocity. Next we will find sorry, mass flow rate. Okay, what is the general formula for mass flow rate? It is nothing but rho ua, right? Yes or no? Yes. But since we are integrating over, since this vz is function of small areas, because the profile is like this, so if you take different cross section, it will be different. So you have to integrate over the whole area. So w 0 to delta dA is nothing but dx dy, right? Fine. So as you can see, this term is only a function of y, and dy, it has nothing to do with dy. So dy, if you integrate it solo, then w comes out, right? So w comes out, then only you are remained with 0 to delta rho vz dx, right? Again, this is nothing but we already derived. This is the average velocity. So you'll get in terms of the average velocity is, just put the value of average velocity, you will get this, right? So this is your mass flow rate. The unit will be kg per second in SI. Okay. What about film thickness? You can easily express film thickness. You take this formula. Just delta is the film thickness. So take delta on one side and rearrange it. So you get cube root of this in terms of mass flow rate. If you want to express thickness in terms of average flow rate, just take the previous formula. Then you will get delta is equal to square root of, it is square root, okay, this is cube root, square root of the 3 mu average velocity, right? So you can easily calculate. Lastly, we'll find, lastly we'll find the force. What is the force on this solid surface because of the fluid here on this also? So that is nothing but the shear stress in the x direction is tau xz, right? It was maximum at this surface. So you have to integrate it, right? So tau xz is a function of your yz area, because the shear stress is applying, for flow is in this direction, but the force, it is applying in this direction. So what is this area? If you take this is nothing but, let's say, take a small area of this, so that will be your dz, right, in this direction, and this direction it will be dy. So you have to integrate this tau xz 0 to w 0 to l into dy dz. Then, but at x is equal to delta, you are trying to find force on the wall, so that will be max at the wall area. So according to coordinate system, this is x is equal to delta, right? It will be force in the z direction, because fluid is flowing in the z direction, so it will apply force on the this bottom surface in the z direction, right? So if you integrate this, at this point, at the exactly surface, that is x equal to delta, you will get the force, required force, right? So just for put the Newton's law, minus mu dv by dx at x equal to delta. You have already this value, right? You've also derived the tau exact, so simply directly you can put tau exact formula earlier and put the, instead of x, just put the delta. So you'll get this, right? So finally you'll get this. So this is your force. You can check the dimensions. So density kg per, you can check the dimensions of this, you'll get the force only. So rho, density kg per meter cube, into meter per second square, gravity, acceleration due to gravity, into meter, the thickness, cos beta dimensionless, then mu kg per meter second, right? So this meter cube cancels, second cancels, right? Kg cancels, kg per meter cube, meter per second square, delta meter. Then I forgot to take L into W, that is your, sorry, there is no viscosity, this mistake, okay, sorry. So you have density kg per meter cube into gravity meter per acceleration second square, into this 3 is nothing but volume, it will be meter cube, and dimension less, so this cancels out. So it is nothing but kg into meter per second square, that is nothing but mass into acceleration, that is force, okay, that is nothing but Newton. Okay, so we found out this is the, what is saying, this is a jet component of the weight of the fluid in the entire film. This is also weight of the entire fluid film. Okay, you now, once you got the average values, you can calculate other values as well, like Reynolds number. Remember, during if you are calculating velocities for this kind of problem, always take the average velocity while calculating Reynolds number. Don't, because Vz is function of this x direction, so you cannot simply take the, put the formula here. So you have to first find out the average velocity, then put in the Reynolds formula, then only you will get the Reynolds number. But the Reynolds number is a little bit different from usual definition. That is your 4 into delta rho z, rho v d by mu, right? Generally it is rho v d by mu, right? Here instead of d it is taken 4 delta. I think this is hydraulic diameter. You can calculate it. Okay. So instead of diameter, because this is open channel flow, right? It is flowing just open, exposed to the atmosphere. So there is no diameter here. So you have to take equivalent diameter. So in this case, it is 4 delta, 4 into thickness. So if you calculate, take the appropriate values, then you'll get something like this. Reynolds number less than 20, you'll get no rippling, laminar flow with no rippling. If in between, then laminar flow with pronounced rippling, and if it is greater than 1500, it is turbulent flow. Okay. Okay. I hope you have understood this problem. If you did not understand, then go read the text. You will understand it. Okay. If you have any doubts, you can ask. Okay. And next class we will discuss again one problem, that is your flow through a circular pipe. Okay. Thank you.